Alright, hey guys, what's going on? So today we are back in our Tensor Calculus playlist. In this playlist, we are going to be talking about an intrinsic equation for the connection. So what I've alluded to earlier has been we have this architecture on spacetime, and on that spacetime we have the connection, we have different types of vectors, the covector and vectors, and then we have the metric tensor. We've sort of developed a lot of this. The next question is there a relationship between the metric tensor and the connection? Because what we've done before is we've sort of related the acceleration of vectors to the connection. What we want to do now is we're going to relate metrics to the connection. So again, if you like this kind of content, make sure to hit that like and subscribe button. Make sure to hit up my Patreon page if this is the kind of stuff you'd be interested in supporting as well. Anyways, let's get into the topic. So today we are going to be talking about the intrinsic equation for the connection. So let's do a review here really quick so that this is fresh in our minds. So initially we started off by saying that the connection was some linear machine, right? It was something that took in two vectors and it spit out a vector, okay? And this was what that vector was. And this vector told us something about the parallelism, or what the sort of the sameness of a vector. If you were to travel along some direction, that direction is given by one of the vectors that's fed in to this machine, and then the actual vector itself that's being transported. And so this gave us, again, some idea on what it meant to be the same or parallel in two different vector spaces. Okay, so that's this equation. We then came across the geodesic equation. The geodesic equation was by virtue of saying the Einstein equivalence principle, that in the frame of within the proper frame, or the frame of yourself at a particular point in space-time, the acceleration is zero, but from an outsider's perspective, acceleration is not going to be zero. And what we found out there is that what we would eventually develop there was the concept of the geodesic equation, okay? We then went on to show that these connections that show up in the geodesic equation and that we regarded as linear machines did not actually transform as tensors, okay? And in doing this, we sort of came about, we sort of started briefly talking about the covariant derivative, but that's something we're going to get more into later. But we really wanted to show that the transformation of the connection did not transform as tensors would have, and so this connection is not a tensor, okay? The coefficient for acceleration, for the acceleration vector in the tangential plane, we were able to show, in this case, that the connection was the coefficient for were indeed those coefficients if the basis vectors looked like this. Right, so this is our acceleration vector. At that point in space-time, we can calculate an acceleration, and the way to calculate an acceleration was through these Christoffel symbols, or the connection, along with the second fundamental form, which is the coefficient on the normal component. And then we were able to give a formula for the connection itself using the metric, using a position, and also using what looked like an acceleration. This is not really an acceleration though, because this analogy doesn't really hold. I'll just erase this. Oops. This is not really acceleration because, again, the acceleration is the double derivative with respect to time, right? So this is really just a double derivative, and so. And it's this right here, right? So the acceleration, you could call it an acceleration if these two mu and nus were the same, right? So if those two mu and nus were zero. So in some sense, this is an acceleration. This is a velocity in some sense, and then we have the metric, and then we have the connection, and then for the second fundamental form, we had this. Let's talk about parallel transport for a second, because this is going to come up again in later videos. We want to talk about parallel transport in later videos, so we want to sort of establish a good intuition about what this is before we dive really deep into it. So we have two vectors, right? So these two vectors, the green one and the red one, this red initial vector and then this one. So we're comparing these two vectors here. These two vectors are not the same from the perspective of someone on the surface of the sphere. Because you can imagine if you're standing here at the North Pole and you look out, right? If you look outwards, then that's going to be the direction of the vector you're choosing, okay? But if you're on the equator and you look outwards, well, your vector is actually going to look more like this red vector, right? Because you're looking outwards. You're not looking up. Right? If you were to look up, this would be your green vector. So this green vector is looking up. The red vector is looking outwards. So parallel transport means that we want to try to keep a vector constant as we walk along the surface. And so in order to do that, we need to, if we're always going to be looking outwards, not upwards, we want to move the vector such that we're always looking outwards, right? We're not ever looking upwards, right? Not ever looking upwards, we're looking outwards all the time. What ends up happening is that there's actually two ways of looking outwards when you get back to the original point. And so there's going to be, and this is how we're going to define curvature, okay? So curvature, in some sense, is going to be defined by the deviation from start to finish at the same endpoint, at the same starting point. That deviation is going to give us it's going to give us information about something like curvature. And the change in this vector and this vector is given by this vector here. So the scale is not great, right? So if you were to take, again, this vector, bring it up to the point here, the difference is going to be a vector that looks like this from the tip of here to the tip of here. And we're just going to put it right here for right now. Right? So we're going to have vectors that point inwards into the circle. These are the this is the change in these two vectors. So in some sense this is a tangential component, and that tangential component is the difference between a vector at this point and a vector at a neighboring point. Okay, so the rate of change of the vector field is always perpendicular to the surface. That's these blue vectors here. Okay, so we saw that we came across this equation before. We had the derivative, and we have this notion of parallelism, and that everything about this notion of parallelism was encapsulated in these coefficients here. These coefficients were the connections. If in the case of the parallel transport this was zero, if this was zero, then this is going to be the case of parallel transport, because all vectors are going to be parallel to each other, right? So the idea here is that the covariant derivative is going to tell us something about the change, and if the connection, if this is zero, then this notion of parallelism, well, there's going to be really no notion of this notion of parallelism is going to go to zero, and so we're just going to get that this equals this. Okay, so this is all somewhat of a little bit of a review, some new things talking about parallel transport. We're going to get into it a little bit later. I just want to sort of establish a firm foundation. Okay. So now we want to develop an intrinsic view of the surface. What does this mean? An intrinsic view of the surface means one way of looking at the surface would be as we are on the planet right now, right? So we are standing on the planet. We don't really have a notion of what a tangential component to our planet is, right? However, if you were to look at our planet from an alien's perspective, you could draw our planet. Here's our planet. Here's our land masses, and here's our water. At any point, we can draw tangential components to the surface. But if we're living, say, on a piece of land here, we don't have a bird's eye view of the planet, so we can't really understand what it means to have a normal vector, right? Because we're already sort of living on the planet. So this is so there's two facts to realize about this before we go forward. So the idea here is that, we're going to have this here, Gij is equal to Ji. This is metric is symmetric, and then we're going to have this also. This is going to be symmetric about the two bottom indices. This is not necessarily going to be the case, though. When we start talking about torsion and torsion-free objects, this is going to sort of fly out the window. Torsion, I'll just write torsion-free also. This is going to... so when we start talking about torsion, we are going... This is not going to work. But we do want to realize these two things before we move forward with this idea of developing an intrinsic view of the curved surface. Okay, so like I said, from an intrinsic point of view, we don't really know what the tangential components are on the surface that we're living, and because of that, we don't have a notion of what an acceleration vector would look like, right? Because again, suppose this is our surface. I'm sort of drawing the planet in a different way now. Suppose this is our surface. From a bird's eye perspective, this surface has a normal component. But if we're standing right here, and this normal component again tells us something about the acceleration of our vector. However, if and with this acceleration we were able to get something that we were able to get these guys. But suppose we don't have this view here. We don't have this vector that we can deal with. Is there an object that we can use to calculate these? And the answer is going to be yes. The object is going to be the metric. Okay? And so let's do this now. So the idea here is we're going to start off with this equation. We sort of established that Gij was the dot product, if you will, between Ei and Ej, right? So if I was equal to j, this would be some number, right? But anyways, and if they were not equal, it would be 0. So we can distribute, we get something that looks like this. The derivative of this dot product, to get from here to here, we're taking derivative of a dot product. This is called metric compatibility, the idea that we can sort of split this up with this derivative. And we'll talk about more about metric compatibility later. But anyways, so we get to this point, and we get to here now, okay, because we've defined our Christoffel symbols as these guys, the derivative of the basis vector with respect to some change in coordinates. So that's these guys. We're also going to change our dummy indices. We're not changing dummy indices. This whole thing right here is this. This whole thing right here is this. And then we can take inner product of these two guys, inner product of these two guys, and we get this. So notice a pattern here. We have K, 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 I, J, I, J, I, and J, and then summing over L's. Okay, so keep this in mind, write it down if you want, pause the video, just remember the pattern here, because now we're just going to change up things a little bit. So this is what we had originally written. I just have these two in different colors, and we'll see why. A lot of this is drawing upon other videos on YouTube as well. But now we have, okay, so J, we have J, so K was here, so now we're replacing all K's with J's. We're replacing all I's with K's, right? So here's an I, so it gets replaced with a K. And then we're replacing J's, right? We're replacing J's with I's. All right, so this is the equation for this metric. Again, we're not really doing much, right? We're just sort of swapping indices. Same here, same goes for this. And so what we get now is when we add these two guys and subtract this, we can do that. We add these two guys and subtract this. All right. But now what we can find is that we can actually cancel out these guys, and we get something that looks like this. Okay, so these two guys, there's two of them. Remember, we're using not metric compatibility, we're using the fact that these two are symmetric and that they're the same. We multiply by GIM, so on both sides, we get this. All right, so now just dividing by 1/2, finding that this is the Kronecker delta, we get this. And so we've come to actually an intrinsic equation now, right? Because everything's in terms of G. Everything's in terms of G. Whereas in the extrinsic case, everything was not in terms of G. We had it in terms of G, but we also had the Christoffel symbol as the derivative of basis vectors within some plane, right? That plane was tangent again to the surface. So this is that equation. This is an equation for our Christoffel symbols. So the picture here, reiterating the picture, here is, so I won't draw everything out, but we have now our connection. We have vectors, we have covectors, we have Gij, right? Gij. Now we have a formula that relates this space to this space right here. The metric here, this right here, connected these two guys together. The metric here, this sort of also connects this space to this space as well, but through Gij. So now we have connections for all three of these things. Well, not really connections, right? There's formulas for each, for this line, for this line, and for this line. Okay, this is the architecture of space-time. And so what we're going to do next is we're going to go over the covariant derivative. The covariant derivative is going to launch us into some more interesting properties about the notion of parallel transport, which is what we've talked about right here. And then from there, we are going to launch ourselves into a series of videos that I think are going to begin to help me at least stand out from other videos. We'll talk about the spin connection as well, which is going to be super interesting. and later videos. But anyways, if you like this kind of content, make sure to hit that like and subscribe button. Make sure to go onto my Patreon page, and I'll see you guys in the next video. Bye.